So far, we have concentrated in this course on pure functional programming. That is, we have always worked just with functions and immutable data. However, in a reactive system of any size, there's sooner or later some state that needs to be changed and maintained, or some state changes that need to be signaled and propagated. To express this, we are going to broaden now our notion of functions to work together with mutable state. We will see that this combination has quite a few repercussions. On the one hand, it gives us powerful new ways to express ourselves in certain categories of systems. On the other hand, it poses considerable challenges how to reason about the resulting systems. So until now, our programs have been side effect free. And one important consequence of this is that we will see that the concept of time wasn't important. How do I mean that? Well, for all programs that terminate, any sequence of action would have given the same result. And that was also reflected in the substitution model of computation. So let's quickly remember what that model was. In the substitution model, programs can be evaluated simply by rewriting the program text. There are a number of rules. The most important rewrite rule covers function applications. So here you see the rule. It says that if you have a function definition, say a function f with parameters x1 to xn and body b, and then later on you have a call of the same function f with actual values v1 to vn, then the program can be rewritten by keeping the application and all the other program elements, but replacing the call by the body of the function b, where all the formal parameters x1 to xn are at the same time replaced by the actual values v1 to vn. So that was the central rule that we had for the substitution model. Now, let's see that in action in an example. Say you have two functions, iterate and square. Iterate would apply the given function f n times on the given argument x. And here you see its right-hand side. Square is just a squaring function that takes an argument and multiplies it by itself. Let's now look at the call iterate of 1, square, and 3. That call can be rewritten as follows. The first thing you do is you take the right-hand side of iterate and you replace the actual arguments for the formal parameters n, f, and x. So that would give you this line here. The next thing that happens is that you do two auxiliary reductions. The first one would simplify the arithmetic expression 1 equals 0 to false, and then this next reduction would immediately simplify the if then else by saying, well, if false, something else something takes the else part. So that's the part that you see here. In the next step, then, we would have to rewrite the call square of 3 of the iterate application. So that would give you, obviously, 3 times 3 by simply expanding the right-hand side of square. An arithmetic simplification gives you this line here, where the 3 times 3 has been reduced to 9. Now you would have another expansion of iterate. So the right-hand side of iterate would again show up here, with the actual arguments replacing the formal parameters, and some subsequent reductions on the if would finally give you if 0 equals 0, that's true, so you would return the then part, and that would be 9. One interesting observation here is that rewriting can be done anywhere in a term, and all rewritings that terminate would lead to the same solution. In fact, that's an important result of lambda calculus, which is the theory behind functional programming. So let's see that in an example. The first result of a reduction in our iterate example was this line here. If 1 equals 0, 3, else iterate 1 minus 1 square of 3. And we rewrote it to this expression here. But that's not the only thing we could do with this expression. Alternatively, we could also have concentrated on the nested call here and rewritten that one. And if we had done that, we would have gotten this expression here. So now we have two different terms that the same term up here can rewrite to. And the important result here is that it doesn't matter which of the two we pick, because in the end both of these terms actually will give the same answer, 9. And that idea that I can rewrite anywhere in a term, but finally all results yield the same result, is sometimes called confluence, because these arrows, they flow together in the final result. And this confluence result has been discovered by Church and Rosser, so sometimes it's also called the Church-Rosser theorem of lambda calculus. Now, all these observations hold in the world of pure functional programming. What I want us to do now is take a step outside that world and introduce state in objects. So why would one want to do that? Well, normally one describes the world as a set of objects, and some of these objects would have state that can change over the course of time. So what does that mean, an object has state that changes over the course of time? It turns out that a very abstract but accurate definition is that an object has state if its behavior is influenced by its history. So for instance, if I take a bank account as an object, a bank account has state because the answer to the question, can I withdraw 100 francs, would depend on the previous history of the account. It would say true if I had deposited earlier enough money so that I could withdraw 100 francs, and it would say false otherwise. So that was the abstract definition of stateful objects. In practice, every form of mutable state is constructed from some variables. A variable definition in Scala is written like a value definition, but with the keyword var in place of val. So you would write var x :string equals abc, and that would give you a variable x of type string with initial value abc. So just like a value definition, a variable definition associates a value with a name. But if you wrote var, so if you have a variable definition, that association can be changed later through an assignment. So you could afterwards write x equals high and give a new value to the variable x. Or you could define a count to be 111 and then add 1 to the count, as you're used to do in imperative programming. So in practice, objects with state are usually represented by objects that have some members that are variables. So for instance, here is a class that models a bank account. We have a class bank account now, and here you see a variable balance initialized to 0, and the keyword private in front says that that balance variable can be accessed only from the methods within class bank account, but not from clients of that class. What methods are there in class bank account? Well, there's the deposit method, which allows one to deposit a given amount of currency units. That amount must be positive. If it is, then it gets added to the account's balance. And conversely, there's the withdraw method that allows one to withdraw an amount that also must be positive and furthermore must be less than or equal to the current account balance. If that's not the case, if for instance, the amount is bigger than the current balance, then the withdraw method would throw an exception with the error insufficient funds. So in summary, class bank account defines one private variable balance and two methods that can be used to change that variable. To create bank accounts, we use the usual notation for object creation. So you would write val account equals new bank account, and that would give you a new account. So let's try out some of these concepts using a worksheet in the Scala IDE. What I've done is I've defined a project Reactive 2 for the second week of the Reactive course, and in there I have defined the class bank account like you saw it on the slide. One thing you notice is in the syntax coloring, variables actually appear in red, which is a good sign that means pay attention. Here's a feature that is at the same time very powerful, but also dangerous. So pay attention to that. So what we're going to do now is interact with bank accounts using a worksheet in the Scala IDE. To do that, I create a new worksheet, call it account. And the first thing to do is create some account. And deposit some initial money, let's say 50 currency units. And that now would respond that an account was created. And what I can do now is withdraw funds. Let's withdraw 20 currency units. So what I see here is there are 30 that remain. Let's do that again. So now it's just 10 that remain, and let's try to overdraw. And we get an error which says insufficient funds. So clearly, accounts are stateful objects because when we perform the same operation, like withdraw here twice, the results differ. The first time we got back 30, the second time we got back 10. And of course that is because the effect of the withdraw method depends on the history of the object, what operations have been performed before on that object. So we've seen that statefulness is often connected to having variables. Let's see how strong or not strong this connection is in a couple of examples. The first example is an implementation of streams, that means lazy sequences, that you have already seen in the previous course in week 7. We have a slight variation here that instead of using a lazy val, we implement non-empty streams using a mutable variable. Here you see how. So the idea is that we have a function cons, which will create a stream consisting of a head t and a computation tail that gives you the rest of the stream when it is demanded. And the way it's done is that the cons function creates a new anonymous class of type stream of t, and it has in that object a variable tail opt, a mutable variable of type option of stream of t, which is pre-initialized to none. Now the tail operation on cons would query the variable tail opt. If it has already some value x, that value is a tail. If it is still set to none, then the tail opt will be computed by calling tail, so this reference to tail will actually invoke this operation and wrapping it in a sum and returning the result. So the question now is the result of cons a stateful object? If you hesitated in your answer, I don't blame you, because in fact, in a sense, both the yes and the no are valid responses, depending on what assumptions you make on the rest of your system. One common assumption is that streams should only be defined over purely functional computations, so the tail operation here should not have a side effect. In that case, the optimization to cache the first value of tail in tail opt and reuse it on all previous calls to tail is purely a optimization that avoids computations, but that does not have an observable effect outside the class of streams. So the answer would be that no, streams are not stateful objects. On the other hand, if you allow side effecting computations for tail, let's say tail could have a print-on statement, then you would see that the second time tail is called on a string, it would come straight out of the cache, so there would be no side effect performed, whereas the first time it would be called, the operation would be performed, including the print-on statement. So that means clearly the operation tail depends on the previous history of the object. It would be different depending on whether a previous tail was performed or not. So in that sense, the answer would be cons is a stateful object, provided that you also allow imperative side effecting computations for tail. Here's a second example to have you think about it. So here we have a class bank account proxy, and it does not contain any variable. Instead, it takes as constructor argument a bank account, and its deposit and withdraw operations would simply forward to that account. Question: are instances of bank account proxy stateful objects? So here the answer is actually more clear-cut. Even though bank account proxy doesn't contain any variable, its behavior is clearly stateful because it depends on the history. All that it does is it forwards to this other mutable bank account. So, for instance, calling withdraw twice would give you different results, just as the original withdraw would have done. So clearly the bank account proxies are stateful objects.